In this problem, we're going to look at converting a line formula to a Lewis dot structure. So basically what we have to remember is how many bonds each element can have, and therefore how many valence electrons it's supplying. So the first compound we're looking at is HCN, and what I'm going to do in red pen here is just write the number of bonds that each element can have. So hydrogen equals 1, carbon equals 4, nitrogen equals 3. So we also need some information from the electron configuration. So let me write that in blue here. So hydrogen supplies 1 electron, carbon supplies 4 valence electrons, nitrogen supplies 3 valence electrons plus 1 lone pair of electrons. So let's go ahead and draw those things out. So we have H with an unpaired electron. Carbon has 4 unpaired electrons. And then nitrogen has 1 lone pair and then 3 valence electrons that are participating in bonding. So really when you're looking at HCN and you sort of read it left to right, you know that the H has to be bonded to the carbon. So let's go ahead and do that. So we're going to pair the valence electron of hydrogen with 1 valence electron of carbon. That remains 3 unpaired electrons on carbon. And so now what we have to do is bond carbon to nitrogen. So let's go ahead and do that in our next iteration here. So I'm going to just bond it to the right. So now if you look, we have 1, 2 valence electrons remaining on carbon, and then 1, 2 valence electrons remaining on nitrogen. So then what we're going to do is just form bonds between those unpaired electrons. So we're going to add a double bond and then another double bond, and so that's going to get us a triple bond. So in building up our Lewis dot structure here, we can say HCN would look like that. So you have your sigma bond between hydrogen and carbon, and then you have a triple bond between carbon and nitrogen, and then nitrogen has its lone pair. So the next molecule is called 1,3-butadiene. And we'll get into this in a later module, but the nomenclature in organic chemistry is very important. So one skill you'll develop is converting a name back to a formula. So in this case, again, we're converting this into a Lewis dot structure. So we'll go ahead and just write down again, hydrogen forms 1 bond, carbon forms 4. We know that hydrogen supplies 1 valence electron, carbon supplies 4. And again, if we're reading from left to right, we're running into a carbon first, right? So let's go ahead and write that carbon down. It has 4 valence electrons, and that carbon is bonded to 2 hydrogens. So let's go ahead and add those. So the hydrogens supply a valence electron, so those are our 2 bonds there. This is 1, this is 2. Now we run into another carbon, so let's go ahead and bond that to the existing carbon. So carbon, then it forms a bond. That carbon has 1, 2, 3 remaining valence electrons. We see that it's bonded to 1 hydrogen. Let's go ahead and stick that in. So H, that supplies an electron. So if you'll notice, this is now bonded, this carbon is now bonded to another carbon, but But you see how we have unpaired electrons here? So we're actually going to form a double bond between those two carbons, but what I want to do first in building this structure up is just get the carbon chain in. So the next carbon that has 3 valence electrons, same thing, it's bonded to 1 hydrogen. And finally, that's bonded to the terminal carbon here. That has 1, 2, 3 valence electrons. It has 2 hydrogens. Let's go ahead and add those in, H, H. And so now when we're looking at our structure, again, we're reading left to right. We have 2 unpaired electrons. We're going to form a bond there. And we have 2 unpaired electrons. We're going to form a bond there. So there's a bond between the 1 and 2 carbons, and then the 3 and 4. And that's where this name comes from, 1, 3. So the start of the double bond starts at 1, then the second one starts at 3. So let's go ahead and finish this off. So that would be the Lewis dot representation. So as you can see, it gets sort of difficult to interpret what that is. So we just convert those dots into actual lines which represent bonds. So when we do that, we can say C, double bond C, H, H, H. There's a sigma bond, and we have a double bond, H, H, H. So that's a little easier to interpret, and if we get rid of the explicitly shown hydrogens and we make them implicit, we can actually represent that molecule like that. So these are 3 different ways of communicating 1,3-butadiene. So this has been problem 1.6 from your textbook, Converting Line Formulas to Lewis dot Structures.